Hi, welcome back. So today we'll be still talking about sound wave here, but we'll be focusing on the Doppler effect. Okay, so let's jump in. So I'm sure you guys probably have the experience that if you are standing by on the roadside, which I highly recommend not to do because it's kind of dangerous. But if you are far away from the roadside and then standing by, if a vehicle comes towards you, you'll hear higher pitch, and then when the vehicle moves away from you, you actually hear a lower pitch. Or maybe you are standing at a train station. When the train's approaching, you hear higher pitch, and that when the train's leaving, you hear a lower pitch. So this is due to the Doppler's effect, where the pitch changes as the source is moving or the observer is moving. Okay, so in this case here, if just let's say the source is moving, so we'll look at the source is moving first, and then the observer is moving, and then also the combine of the two, okay, at the end. So when the source is moving, so you can see that the waves emitted by the source actually get pushed together when it's the source is moving towards the observer. On the other end, if the observer is on the other end here, and so the waves emitted by the source actually that they are furthest away separated. Okay, so in that case, um, mathematically we can analyze this. So if the source is moving, so then at each time period, it will give you out a new, say, wave peak or wave um, valley, depending on which one you are talking about. But let's say let's focus on the peak of the wave. Okay, so at this one, it emits wave one, and then at the second location, a period after that, the source has been moved to position two. The wave peak it gives out will be the second one. So in this case, you can see on this side, wave peaks are pushed together, closer together. On the other side, they are further apart. Okay. And that's just focusing on two time instances for the fifth one and the sixth one. Okay, so for the fifth one to emit it, so if the source is not moving, so then we can see after one time period, the peak will propagate the distance of v for the speed of the wave, sound wave here, times the period sub s for the source. So in this way, and then also in that way, the other way around, okay? Now, with the source being moving, now your source is at location 6 after t period of t time equal ts. So now your source is over here. So now the source is now emitting as another wave front or wave peak from this location. Okay, and if the observer is standing over here, so the first time it hears one wave peak, and then the second time will be by this one, but will be closer. Okay. So this second peak now will just have to travel shorter distance. In the observer's point of view, the wavelength it becomes smaller. Okay, so by amount of this distance traveled by the first wave peak minus the distance traveled by the source. Okay, so u for the speed of the source. Okay, in this case. So then lambda becomes this guy minus this guy. We have the same t of s. So then it will be speed of the sound minus the speed of the source, which we use a different notation here, u sub s. Okay. So that's the new wavelength. So based on this new wavelength, so then because it's smaller, so then when the source is approaching the observer, we will hear higher pitch because wavelength and frequency are inverse proportional to each other. On the other side here, so if the observer is standing on the other side here, then the wavelength of the wave actually appears to be longer of this distance plus this one. Okay, so then lambda will be u plus mu s ts. Okay. So depending on if the source is moving towards the observer or away from the observer, the wavelength appears to the observer will be equal to V plus minus US times TS. Okay, and TS is inverse of frequency in that case. For the minus will be approaching, source is approaching the observer. For the plus sign, it will be the source leaving or moving away from the observer, okay, in that case. Now, if we do the frequency, the observer hears or feels, so then we do V, speed of the sound over the lambda. So it's V over this whole thing together, or over this, okay? V over this whole lambda. So this guy will flip up, becomes this, and then V over the V plus minus US, okay? And if you divide both numerator and denominator by V, so then on the top here will be just 1, and then here will be 1 plus minus U of S over V. Okay, so this is speed of the source over the speed of sound. Okay, so then it's a ratio of that. So if you are, again, moving towards, the source is moving towards the observer, you take the minus sign, so then you get a higher frequency, okay, by the observer, and then you do plus if the source is moving away from the observer, so then the observer will hear smaller frequency, okay, so in that sense. All right, let's take a look on the example here, the first one of the day. So this one says a bat moving with speed of 3.25 meters per second, emitting sound of 35.0 kilohertz. Okay, so that's kilohertz. We need to take a note of that. And so and then this guy emits sound. Okay, so this is the source moving, so U sub S. Okay, and then this is the frequency of the source. Approach the moth at rest on the tree trunk. What's the frequency heard by the moth? So the moth is the observer. Okay, and then B, if the speed of the bat is increased, is the frequency heard by the moth higher or lower? C, calculate the frequency heard by the moth if the bat now oscillates to a speed of 4.25 meters per second, and use the speed of sound as 340. Okay, so that's V. So for A, this is the source is moving, so frequency by the observer, F sub O, then will be 1 over 1 plus or minus U of S over V times F of the source, okay? And in this case, because this is approaching, the source is approaching, so then we'll take the minus, okay? In that, so it's minus of that, okay? All right, so we can plug in our numbers, 1 over 1 minus the 3.25 over 340 and times the 50.0 kilohertz. Okay, so you can keep the kilohertz, so the answer will be in kilohertz. Okay, so this will give us 35.3 kilohertz. Okay, so the mouse is hearing higher pitch. Okay, if it hears at all. Okay, all right. So in part B, so we know that because F0 is equal to 1 over 1 minus US over V times Fs, right? So everything else stays the same, but this US increases, okay? So if that's the case, then US over V will increase because V stays the same, okay? So this guy will increase. Then 1 minus of that will be decreasing, okay? So your denominator as O is decreasing. So then 1 over that will be increasing, okay? So everything will be increasing. So we just kind of rationalize that it should be increased, okay? Okay, on that. And in the next part, we'll just be verifying that, okay? So basically, you're doing what you did in A again, but just changing the US to be 4.5, okay? So the F0 should be 1 over 1 minus, instead of 3.5, you do 4.25 over 340, and then times that 35.0 kilohertz, okay? And this gives you 35.4 kilohertz. Okay, so just a little slightly larger. Okay, so indeed it increases. Okay, all right. So let's go back. Now let's take a look when the observer is moving in this case and the source is stationary. Okay, so it'll be pretty similar. So if observer is moving, now again the um, the waves or the sound here by the observer from one peak to the next peak, okay, it will become actually the distance that observer has to travel actually will be smaller because the observer is moving towards the source, okay. And then when the observer is moving away from the source, then the distance that the observer travel or hears from one peak to the next peak will be actually longer, okay. So in that sense, and then mathematically, you can do the same. You can do the same analysis, okay? But it will turn out slightly different for the expression. So we are just going to skip the derivation, but looking at the answer or the conclusion here. So for the frequency heard by the observer, again, as f sub o is equal to 1 plus minus. Now u sub o, that's the speed of the observers moving. And then over v, again, that's speed of sound times f of s, again, the original frequency emitted by the source. So in this case, we'll take a plus when the observer is approaching, and then we'll take the minus when the observer is moving away. Okay, so this is it then the other way around. Okay, comparing to the when the source is moving, the observer is not moving. Okay, so be careful about picking the signs. Okay. All right. Again, we'll take a look at the example here, and then we'll move on from there. Okay. So the second one here, it says when the bell in a clock tower rings with a sound of 475 frequency. So this is your source frequency f of s. Okay. The pigeon roosting in the belfry flies directly away from the bell. The pigeon hears, so this is the f of o. What's the speed of the pigeon? So it's asking you what's the observer speed. Okay, so and use the speed of sound. Okay, so this is again the v. All right. So in this case, the observer is moving. So then frequency uh, heard hears by the observer is equal to 1 plus minus u of o in this case over v and times f of the source. Okay. Now you can see f of o because it's this observer is flying away, so we'll take the minus. Okay. So we'll take the minus. Or let me just maybe say we'll take the minus, so not the positive. Okay. All right. So we are looking for u of o, so we can just plug in numbers here. So 448 hertz by the pigeon is equal to 1 minus mu of 0. We are looking for over 340. And this should be in meters per second. So then u will be in meters per second. Okay. Times 475 hertz. Okay. So we'll just solve for u0. Okay. So we'll divide both sides by 475. Okay, over 475 there. And after that, you'll just move this 1 to the other side, so -1. Okay, so then we get 448 over 475 -1 equals to minus of u0 over 340. Okay, then we'll do that. That means multiply both sides by -1 and then times 340 to both sides of the equation. Okay, times 340 to the left-hand side as well. So then we'll find out u of o is equal to 19.3 meters per second. Okay, that's the speed of the observer's moving, which is the pigeon. Okay, all right. So if we combine the two, when both the observer is moving and the source is also moving, so this typically happens if um, a police car is following you or someone else. Okay, so then um, for the police car or for the police to determine if you are speeding, they will emit wave, okay, sound wave radar from the radar, and then that actually will hit your car and comes back. So there's a two-part process here. But when you hear, if you hear it all, or if you can receive it at all, then you'll hear the frequency there. Okay, so in case, so you'll have to do that twice. If that's the scenario for the police car, determine that. So observer now for the car, or the person in the car receives the frequency equals to V plus minus U of 0 of O. This is the speed of the observer, and then over V plus minus U of the source times the frequency emitted. Okay. So depending on if the two vehicles are approaching each other or one is moving away and then the other one is approaching. Okay, so if you are it's being chased or if you are moving in the opposite direction. Okay, and then you'll take the either plus or minus and in the numerator and also in the denominator. Okay, so we'll look at the source first, and then the observer after that. All the other way around doesn't really matter. Okay. And for the police car to receive that back, so then frequency by here by the car becomes f of the sub s, and then reflect back to the police car. Now police car becomes the observer. Okay, so there are two processes here. But let's take a look at this one here. So it says a motorcycle and a police car are moving towards one another. The police car emits sound with a frequency of 523 Hz and has a speed of 32.2 meters per second. The motorcycle has a speed of 14.8 meters per second. What frequency does the motorcyclist hear? Okay, so for that, let's go to this one here. All right, so F of the observer is equal to V, speed of the sound, plus minus U of O on top, okay, and then V plus minus U of S at the bottom times Fs. Okay, so they are both towards each other. So that means in the denominator, you want to pick the sign that makes the frequency bigger, which then will be the plus. Okay, so we will take out the minus. And then in the numerator, you'll do the same. You'll pick the sign that will make this frequency bigger because now it's towards. Okay, so then the plus will go away. Okay, so and then we can plug in numbers now. 340 plus for the observer, which is the motorcycle, 14.8, and then at the bottom 340 minus 32.2 for the speed of the police. Okay, times 523 hertz. Okay, so yeah, it's about which sign you'll pick. Okay, so at the end, this is 603 hertz by the motorcyclist. Okay, and then if we are looking for what's this frequency received back by the radar on the police car, so then this becomes the new f. So in that case, this becomes the new f of s prime. So then for the f of o prime, you'll do again 340. Now this guy becomes u of o prime, and this guy becomes u of s prime. Okay, so then plus 32.2 on top, 340 minus 14.8 at the bottom, and then times 603. Okay, and that would be the frequency heard by back by the radar in the place. Okay. All right. So I think that would be it for today. So or actually a couple more things before we end this chapter, but just quickly. Okay. So so in the equation we used earlier, maybe we can go couple slides back here. So when we take the minus sign in the denominator, right? So um, as long as this guy is less than the speed of sound, there's no problem. But when this speed of thought um, gets closer to the speed of sound here, then we can see this denominator becomes approaching zero. So then this whole thing will become very large as if the denominator becomes zero. Okay, so that happens. You can see that for the moving source, if it's approaching speed of sound, so this observer's frequency becomes very higher. Now for the numerator, it doesn't matter; it will be just linearly increasing. Okay, so when the speed of source approaches the speed of sound, then this guy, the frequency gets very big, and then it's actually creating a sound boom, which is called sonic boom. Okay, so there's a video under this link here. You guys are welcome to click on that and watch the video. It's pretty interesting. Okay, so when that happens, you have create sonic boom and make a very loud noise, not for the source, but for the observer. Okay, nearby. All right. Um, and next section talks about the hearing mechanisms. So you guys can read it on your own. Basically, how the eardrum works and the signal being transported to the neural system in your head. Okay, and then the application of the sound, specifically for ultrasound in the medical field. Okay, so this is a ultrasound picture of a baby in the womb there. Okay. All right. To summarize, so mainly we talk about Doppler's effect today. So if the source is moving, then so this will be just like one single equation to use, and in both scenarios, if the source is moving and the observer is moving, okay, but you have to pick plus or minus sign there. If you just have the sources moving, observers not moving, and this guy becomes zero. Okay, so then you just have to pick whatever sign you need here. If the observer is moving, source is not moving, this guy becomes zero. Okay, so then this equation still applies. If both of them are moving, then you have both of them in the equation. Okay. All right, so that will be today for that will be it for today, and we'll come back another time. Okay.